Hello and welcome to another video from sickmaths.co.uk, where you can find so many free math videos. This one's about F equals ma while something is moving. So F equals ma is just a formula for force, and we can have situations like we had in another video where we've got equilibrium, i.e. it's not moving, but this one's about when something is moving. So here's basically the question with a bit more information, like the coefficient of friction is 0.2. That just means how rough the surface is, and what we actually want, which is find the acceleration, please. So what do we have in this diagram? We've got a particle here which is on a slope, and another particle that's hanging freely, and they're connected by a string, not an elastic string but a taut inelastic string, which goes over a pulley, as it says here. You need to be used to these kinds of questions. You'll see a lot of them like this. What else is there? Okay, so there's frictional force Fr going downwards, and they're called particle P and Q, and T always stands for tension in the string. What else is there? It's at 30 degrees, this slope, and just by looking at this 4g, you should know that the mass of the particle is 4 kilograms, and that's why the weight shown by this arrow is 4g, because the weight is 4, the mass times, the weight is a force, sorry, like F equals ma. So F is equal to mass times acceleration, and so the acceleration due to gravity on the object is what we call g, which is 9.8. So that's why you always say weight is mass times acceleration. And you do the same here. So the mass obviously for this is 3 kilograms, and that's why the weight of it is 3 times g. Okay, that is the force on this object, but that does not mean it's accelerating at g, because there's other forces on it to slow it down or speed it up. What else? Oh, there's a reaction force here that we talk about as well. Cool. Yep, so let's get started on the question. Forces on P over here. T minus friction. So T is the thing that's pulling this force up, okay, because they're assuming it's going upwards because of the acceleration being in this direction. That's another thing we didn't mention. So you got T going that way and pulling it up, and friction working against it, and also you can break up the weight force into its components, i.e. perpendicular to the plane or along the plane. So the weight force along the plane is going in the opposite direction to the acceleration of the entire system. Do you know what I mean by the entire system? That means they're all connected together, aren't they? These two particles on the string, so the all of that is called the system, isn't it? So it's the weight force is going against it, just like the friction is going against it. The only thing going with it is the tension, and the resultant force is not going against it or away from it. It's simply because it's perpendicular to the force. There's no component of this force that is going in that direction or that direction. But it is important because the amount of reaction force affects the frictional force, because frictional force is equal to coefficient of friction times the reaction force. Okay, and you could look back into our video of F equals ma in equilibrium to understand why the reaction force is important to the frictional force. But very briefly, if you're dragging a heavy object or let's say you are dragging a light object, but you push it down into the ground while you're trying to drag it forwards on this rough surface. The frictional force is going to be greater, isn't it? But if you've got even a heavy object and you're almost lifting off the ground, because it's hardly touching the ground, there isn't going to be much frictional force. So it doesn't matter so much what the weight of the object is, it matters what the reaction force is at the end. Now, since there's no force, there's the weight force, but it's on a slope, that can decrease the reactional force, because it's sort of the higher the slope, the more it's like falling down and less touching the slope itself. Yeah. So, or I should say another way is that the greater the angle of the slope, the greater the component going along the slope of the weight than perpendicular to it. So that means it decreases the reactional force and increases the force going along the slope. Wow, so much explanation. Anyway, so here we go. So you've got your T, which is pulling you that way in this case, and the frictional force and the weight force going along that way. And if you want to know why it's 4g sine 30, you're going to have to also look into the F equals ma while in equilibrium video on this website, sigmas.co.uk, in the A-level section. Okay, so writing F equals ma means you do T minus frictional force minus the weight force along the slope equals mass times acceleration for that object. So the mass of that object is 4, and acceleration a is what we're trying to work out, so we just write a. So that is one formula. Oh, I've actually simplified it a bit. What have I done? Oh yeah, the frictional force I've replaced with mu r, the coefficient of friction times the reaction force. Okay, and again, how did I get the reaction force is 4g cos 30? Well, it's to do with this angle, and it's you normally just say 4g cos 30 is your reaction force depending on the weight. Yeah, it's quite easy to see that once you practice it, but again, look at F equals ma while in equilibrium to understand the details of that. Okay, so that is one formula, and forces on Q. Where's Q? There it is, Q. What are they? Oh, that's really simple, because there's only one force going that way and one force going that way. No reaction force, no other force. So 3g minus t equals mass times acceleration, so the mass of this object is 3 times acceleration, which you still don't know. Right, now the other interesting point is, how comes tension is going that way and that way? Well, actually, it's the same tension throughout the rope, okay, and this tension over here represents the force forces from this object on this object, and but whatever that force is, it has to be the same as this force, which is also pulling it as well. So maybe that sounds a bit weird, but you have to just remember tension effectively goes both ways depending on which object you're looking at. So just get used to it for now, if that expression didn't make sense, that tension is going that way and that way. Always. Now, we do simple, we've got a simple case of simultaneous by elimination, i.e. just adding the two formulas together, and since you've got t minus, and so you've got t there and you've got a minus t there, when you add them together they disappear, so you end up with this plus minus this stuff, yeah? Because you just write it as 3g minus 0.4 blah 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 minus that as well, and adding these bits together as well. 4a and 3a gives you 7a, and then rearranging all of this just to make a the subject, i.e. bringing that 7 underneath, gives you this. Oh, I've just simplified 4g sine 30 as well to 2g, because sine 30 is just half times 4g is 2g. So that's just a little bit simplified there, but you could simplify it more. 3g minus 2g is 1g. Could even simplify that very simply. That's root 3 over 2, whatever. But anyway, so you stick it in the calculator and you get this answer, 1.3 meters per second squared, and that is the answer to A. Anything else to explain? Oh, that's the unit. You write meters per second squared, or seconds to the minus 2. That's the standard unit for acceleration. That double arrow is a standard way to express an acceleration. And that is it, really. Thank you.